Hi everyone, I'm Tal, and I'm going to be talking about our work on symbolic querying of vector spaces. So we're going to be talking a lot about knowledge graphs in this work, and knowledge graphs are basically this form of data where you have a bunch of nodes or entities, which could be people, places, things, and then you have directed edges connecting these entities. So which give kind of facts about them. So, for example, Steve Jobs is a fan of Bob Dylan. That's an edge. Steve Jobs lives in the United States. These knowledge graphs are kind of everywhere. Every big tech company or Amazon, Facebook, Google, that kind of thing has their own knowledge graph that they basically collect from their own data. So, what can we do with knowledge graphs? Well, you can think of a knowledge graph as essentially being a simple database system, right? The tables can only have two columns. Um, well, what do we do with database system? These are incredibly popular. They're used by basically every IT company in the world. And why is that? Well, it's because you can ask incredibly interesting and complicated questions, right? If you have a database, you can pretty much ask whatever you want of it. Um, and you have these powerful languages like SQL, which let you do this. And that's kind of the big reason that they're so popular. So this should be what we do with knowledge graphs too, right? Well, no, actually, research into knowledge graphs basically doesn't talk about this at all. What the community focuses on mostly is this task called link prediction. And basically, the idea is that knowledge graphs are very sparse, right? There are tons and tons of possible facts, and they only describe a small portion of them. And the difficulty there is that most facts in general won't be true, right? If you pick two entities at random and you pick something to relate them, it probably won't be true. But it's very difficult to differentiate between facts that we just haven't gathered and facts that shouldn't be true. And this task is called link prediction, where you try to predict whether or not an unseen fact should be true. Um, and the way that this is typically handled, kind of the state of the art way, is you take every entity and every relation and you embed it in vector space. So you treat it as a point in vector space. And then you have some function f, which is part of your learning phase. And this function f makes some simplifying assumptions such that it can take the vector representation of two entities in a relation, and it can predict, basically gives you a score of how confident it is that that fact is true. Okay, so what do we do then in our work? So our contribution is basically we want to go from these relational embeddings to something approximating what we do with relational database systems, right? Which made them so popular. And how do we do this? Well, we propose the first probabilistic model of relational embeddings that is designed specifically around querying and not just link prediction. What do I mean by that? We define querying semantically. So there are a couple other pieces of work that have looked at this task, but they define it as just kind of another machine learning task that you learn from data. And that's not quite how we do it. We treat querying kind of as a baseline for building our model, and it's efficient by construction. Okay, so in order to do this, a big tool that we're going to borrow from the database community is this thing called a probabilistic database. So a probabilistic database is essentially a model where you take a standard relational database and every row gets annotated with a probability. Now, it becomes a probability distribution over relational databases where you treat the rows as independent random variables. So this is a example of a relational database. It has a probability equal to the product of the rows that are true. And you define kind of a full probability distribution in this way. And since you already know how to query each of these resulting relational databases, you can take an expectation over them to compute whatever query you want. And kind of the main insight here from probabilistic databases is that they give you a semantics for pretty much whatever query you want, but only some of them can actually be computed efficiently. Okay, so how are these probabilistic databases related? Well, we can think of relational embeddings as essentially being probabilistic databases in disguise, right? So we can take the entities and relations in our knowledge graph, and anytime we want to fill in a row with a probability, we can use that function f with the embeddings of the row and actually compute that. And depending on exactly which embedding, you may have to convert it to a probability, but you can get a prediction. So what we propose is tractor, which so essentially the idea is that we take the simplifying assumptions from relational embeddings that give them predictive power, and we actually incorporate them inside the probabilistic database at that level. And the way we do that is we just essentially assume that every relation has a form where it factorizes. So a binary relation is expressed in terms of latent unary relations. So each entity gets a relation deciding whether it participates in a triple, and the same thing for a relation. And you can kind of construct the database that way. And the key insight here is that this assumption makes a lot more queries efficiently computable and a lot of useful queries. But there's a catch, right? If I go back to that picture that I had where you were embedding each entity as a point in space, well, right now this is only in one-dimensional space because you only get one probability for each entity. So how do we get around that? Well, we use mixtures, right? So we have lots of these models with different parameters per dimension of the mixture, and we average over them. And this is kind of the natural thing to do when you want to improve expressiveness and still maintain that efficient querying that we were talking about. And you can also view this now as, if you take a single entity, you take your Steve Jobs and you look at its probability across different dimensions of mixtures, that's your embedding vector. Okay, so how does this perform on link and query prediction? We know now in principle that it should be expressive, it should be efficient. So how does it do? Well, in terms of link prediction, we can actually show that this mixture is essentially equivalent to distmult, which is an existing link prediction algorithm. And in fact, it's one of the best ones out there. So our model will do well on link prediction. In terms of query prediction, we compare it to one of these models, which does, as I mentioned earlier, treats querying as another machine learning task. We use the same setup where you generate queries, and we find that it's very similar, despite the fact that we're not treating it as another task. It's just part of our model directly. So, in conclusion, kind of the little takeaway that I want you to get from this work is that when you're dealing with uncertain relational knowledge bases, probabilistic databases provide a kind of clear, well-studied, it's been worked on for 20 or so years now, semantics for doing reasoning, for actually querying, going beyond link prediction. And incorporating the factorization assumptions from relational embeddings back into the probabilistic databases allows you to get efficient inference for free in a lot of cases where you didn't have it before. Thanks.